So I'd like to welcome everyone to this latest seminar from the Materials and Manufacturing Group at the University of Glasgow. My pleasure to introduce Dr. Zhaofei Xiao, who's currently a project officer in advanced material technology at Best 2020, the new technology transfer center at Swansea University. Zhaofei's research spans composites design and manufacture, finite element analysis, experimental mechanics, process automation, and material characterization. Zhaofei was previously a research associate at the Materials and Manufacturing Research Group at the University of Glasgow from 2017 to 2020. Prior to this, he completed his PhD in composites design and manufacture at the University of Nottingham. The title of today's presentation is Low-Cost Manufacture of Steered Fibre Laminates, and I'll leave it to Zhaofei to tell you more about that. So, Zhaofei, over to you.
Okay, thank you very much, Phil. Hello, everyone. Please let me share my screen now. Yep, can anyone see my screen?
Yep.
Yep, good. So, thank you very much, Phil, for the brief introduction for myself. It's my honor here today to present the achievement of the SteerFab project, which I did when I was in Glasgow. So, sorry, the team, the SteerFab project was funded by EPS-RC, and it's led by Dr. Phil Harrison at the University of Glasgow. I was a research associate in the project, but unfortunately, I left Glasgow about 2 months ago. I was replaced by the two new research assistants, Lee and Paul, to carry on this project. And this project was collaborated with other two universities, Bristol and Manchester. And this project is also supported by the two industrial company, ESI Group and the Dassault System. And this project also supported by the three R&D centers across Europe, like the Simpcomp Composites Manufacturing Hub at Nottingham, and NCC National Composites Center in Bristol, and the Institute of the Science and the Innovation in Mechanical Engineering in Portugal. Okay, firstly, please allow me to briefly introduce the background of this project. So most of the advanced composites are manufactured by some stacking straight fiber plies at a certain specific angles, like 0, 90, plus minus 45. However, the lack of the choice of fiber angles limits the full potential of the composites material. So, but since a few decades ago, research are focused on the development of variable stiffness panel, which contains the steered carbon fiber in the composites to achieve the better mechanical properties. There are two main types of manufacturing process to manufacture variable stiffness panel. One is a conventional automated fiber placement AFP, and it's a new variant, which was continuous tool sharing technology, which is developed in University of Bristol. However, in the AFP made variable stiffness panel, we normally have some defects like the overlaps and the gaps, which will influence the mechanical property of the composites. And both the CTS and AFP machine have the low production rate because they have to deposit carbon fiber toe by toe and layer by layer. Hence, it will cause a high manufacturing cost together with the high capital cost of the complicated AFP machine. So in this project, we want to develop a low cost and a rapid forming process to manufacture the steered fiber laminate without any defects. And in the meantime, we also want to develop a numerical tool to support the design, analysis, and the manufacture the steered fiber laminates made by this new forming process. Okay, so all the story came from the manufacturing trial did by Dr. Phil Xiao a couple of years ago. So pen woven glass fabric is manipulated by hand and is on a table and clamped by some G clamps around the parameter. So we can see the some cavalier fiber pass in this fabric. So it's potentially maybe the promising method to manufacture the steered-fibre laminate. And also, Dr. Phil has also developed a verified code previously for modeling the variability of the toe orientation in the engineering fabric. So this project is established on the basis of these two previous studies. So I will introduce the achievements of this project from four aspects in this presentation. We will start with the development, the numerical development tool, SteerFab, and followed by the manufacturing process development. Then I will show you some numerical simulation and experiment data. And the last, I will show you some exploration for the application of the SteerFab laminate. Okay, let's start with the development of the SteerFab code, the numerical tool. So the SteerFab is developed on the basis of the verify, as I mentioned before, but now it can automatically generate the steered pattern and its corresponding unsteered fab shape. And it can also generate the laminate layout containing both straight and steered fiber paths. Then the code can automatically extract the element information from the FE model and then map the fiber orientation, fabric thickness, this information on the model. Then we can conduct mechanical analysis in the software, like the abacus. Okay. And we have several important functions in the code. The first one is the pattern generation functions. So we use mathematic functions to define the shear angle along the horizontal center line from the center towards vertical edge of the pattern. So through change this mathematical function, we can generate various types of the steered patterns. Then the code is able to create straight, steered, or hybrid laminates and superimpose all the information in the one input file and input it to the abacus to the simulation. And the code is also can visualize the shear angle and the fiber orientation of the pattern you just generated for the user's convenience. And the last but not least, the code have the 2D forming functions. So these functions helps user to understand how the fabric can be manipulated and formed from its original shape to the target steered shape. So the user can use their mouse to select the points, the nodes from the kinematic model. Then the code can automatically generate the position of the initial and the final position of those nodes and indicate their moving path. Okay, when we're talking about the manufacturing process, as I mentioned before, the story came from the initial manufacturing trial. Then we used a type displacement method to manipulate the fabric. So we cut the fabric into its initial shape and also made some type around the parameters. Through displacement, those types in a certain sequences, we can achieve the steered fabric. However, this method got a main drawback. We have the lack of control of those points inside or around the parameter. So in order to solve this problem, we proposed a new method, which is called multi-point manipulation method. So the idea is by pulling some control points as within or on the parameter of the fabric to their target position, so we can achieve the steered fabric sheets. So at each select manipulation point, so we use nylon line to pierce through those points, and those nylon line are also thread through some holes drilled in a bespoke sheet. The position of those holes are the final position of the associated node on the final target steered pattern. And to solve the potential damage around the control point, so we also thread the button on the fabric to reduce the stress concentration. So by after we promote this proposed this new method, it brings our three important questions to answer. The first one is how to back select those points, and what's the repeatability of this process, and does the manipulation order affect the final steered pattern and the generation of the forming defects like the wrinkles. So to answer those three questions, we designed two experiments to understand the process repeatability and the effect of the manipulation order. In both experiments, we select a steered pattern, and we divided it into 5x5 grid with control points at each corner. So then we use the SteerFab code to predict the initial and final position of those control points. So in the repeatability test, we designed a manipulation order, which the number on this figure is showing the manipulation sequences, and this test was repeated 3 times, and we took the picture after each manipulation step and to compare the fabric shape at each repeat. So if we go through the repeatability test from 3 samples, you can see at each manipulation step, the fabric have the similar shape. So if I go through the whole process, and if we compare their final steered pattern, we see they are quite similar, and the location of the wrinkles created by the manipulation are also the same. So it indicates this process have good repeatability. So the next step is to understand the effect of manipulation order. We designed 3 orders. Order 1 is we just used for understand the repeatability, and order 2 is we start to manipulate some nodes around the parameter first, and then toward to the nodes at the center. And the order 3, which is a complete reverse order of order 2. So with this time, we start to manipulate the node around the center, then toward to the outside. Now, if we compare the final steered pattern from the 3 orders, we can say in the blue regions, order 1 and the order 2 have the wrinkles in that regions, whereas order 3 don't have those kind of wrinkle. The reason could be the development of the wrinkles during the manipulation process. So please let me to explain. So if we go through the manipulation process, so after we done the first manipulation, in order 1 and order 2, we can already see the large scale wrinkles along the vertical center line, whereas the order 3 don't have that kind of large wrinkles. And these large wrinkles is still exist in order 1 and order 2 until the final step, but order 3 doesn't give a chance to form the wrinkle along the vertical center line. And also, if we compare the final steered pattern at the center region, which is indicated by the red frame, all these 3 patterns, all of these routers will have the large scale wrinkle in that region. The reason is that the displacement paths of those 4 nodes at the center are all towards to the center. So it will introduce the compression to the fabric. Hence, the fabric is likely to generate the wrinkles. So from the experiment we done above, we know if we want to eliminate the wrinkles, firstly, we must avoid the large-scale wrinkles generated earlier in the manufacturing stage. So to do that, we need to manipulate the points which have the smallest displacements first to constrain the fabric so that the later manipulation are less likely to reintroduce the wrinkles. And the second method is to select the control point, which applies the tension rather than the compression to the fabric during their displacement. And the third method is we can apply some surface constraint. So during the manipulation, we place the fabric between the perspective sheet and the surface of the workbench. So we apply some surface tension so to eliminate the wrinkles. Then we select 3 different types of fabrics: 2 glass fabric, 1 carbon fabric, and we redesign and we reselect all the control points to make sure all the manipulation, all the nodes will apply the tension to the fabric. So if we compare the result, we can say the wrinkles were significantly reduced, and the experimentally manufactured fabrics match the predict steered pattern very well. So that's a very good achievement. And in order to further develop this manufacturing process, we teamed up with University of Manchester. We want to manufacture a new type, a bespoke type of fabric with bespoke toe spacing and thickness to improve the steerability, leading to no wrinkles to the fabric. And we can also use the robot to integrate some tufts on the fabrics as a control point instead of using the current button and thread method. So because the tufts are integrated on the fabric structure, so they are expected to eliminate the potential damage around the control points. Regarding to improve the production rate, if we compare the manufacturing time with the current button thread method and the potential new fabric, the production rate can be improved by 300%, because we don't need to manually to do the threading, which will significantly improve the production rate. So after we know we can successfully manufacture this steered fabric, so we want to understand whether it's truly useful. So we conduct a numerical simulation and followed by the experiment to verify the result. So all the simulation work is inspired by some previous studies from other researchers. Then at the first stage in this project, we conduct the screening investigation to understand the influence of the steered pattern, starting sequences, and the geometry of bucking load. We select the mathematical function, which is showing on the left-hand side, to generate the steered pattern, and we give the a range for the variable, which is sigma max. Sigma max is the shear angle along the vertical center line, and it's the intersection of the vertical center line and the horizontal center line, and the vertical edge of the pattern. So, and we investigate 2 geometries. One is a flat panel another one, the panel is the same size but has a hole at the middle. At the stage 2, so the best performing laminates will be selected to do the further linear post-buckling simulation to understand their failure. So both the carbon fiber and the glass fiber composites are investigated. So I should mention that in the simulation, we want to keep the mass of the steered fiber laminate is the same as the mass of the straight fiber laminate, because when you share the fabric, you basically increase the areal density of the fabric. So in the simulation, we increase the thickness of the straight fiber laminate to compensate that mass increase in the steered fiber laminate. So the thickness of straight fiber laminate equals to the original thickness times by the number of the ply and times by the compensation factor. Compensation factor is just the error ratio from its initial stage to their final steered pattern. Then we, in the simulation, will also assume the fabric is an incompressible material, hence the thickness of steered fiber thickness equals to original thickness divided by the cosine theta. Theta is the shear angle of the fabric. So if we look at the result of the numerical simulation, we found when the sigma max reach at 30 degree, we achieve the optimum steered pattern, and we found the hybrid laminate, the SFP 90, this hybrid laminate offers the best buckling resistance, and the conventional QI laminates was the best among the straight fiber laminates. And the improvement ratio of the hybrid laminates is 5.4% compared to the conventional QI. And if we look details of the buckling data on the two panels, one with the hole, one without the hole, we can say if we have the hole at the middle, it will decrease the buckling load to all the panels. However, if we have the steered fiber laminates in the composites, we found that we reduced the negative effect from 10% in the straight fiber laminate to about only 5%. And if we also compare the buckling load of the best hybrid laminates and the QI laminates, the improvement ratio becomes more significant to 7.4 compared to 5.4 previously. Then we conduct a post-buckling simulation to understand the failure. The results shows both buckling load and the failure loads can be are improved by the hybrid laminates. The improvements are slightly different between the carbon fiber and the glass fiber composites because the difference in material properties. And the reason for that, the reason for achieving the better buckling performance is if we continuous changing fiber orientation in the steered fiber ply lead to a more uniform stress distribution and a lower stress level compared to the straight fiber ply in the coastal isotropic laminates. And the steered fiber path can redistribute the load from the highly loaded central region towards to the edge, which are more stiffer, but due to the boundary condition because out of plant disciplines are fixed and the fiber orientation. So the hybrid laminates can achieve the improved buckling and failure load. Then, after we determine the optimum steered pattern, and we manufactured one and conduct the buckling test and compare the results against to the numerical simulation. And I should mention that in the new simulation, we I did some modification, and firstly, we use two thickness assumption methods. The first one is that we used before. We assume the fabric is incompressible material, but it's overestimates the thickness of the fabric because we ignore the fabric compaction. And the method two, so we actually measure the thickness of the shear at a different shear angle. But if we use this trend, we will ignore the change of fiber volume fraction. The reason to doing that, because we here at this time we didn't scale the thickness of straight fiber to compensate the mass increase in the steered fiber laminates. Because in reality, it's very difficult to compensate that only around 5% mass difference by simply add or remove apply in the laminates. So here's some comparison about the buckling mode and between the simulation and the experiment and the failure locations. So we can say we achieved a good agreement between the simulation and experiment. If we look the actual data, so we found both in the simulation experiment work, the steered hybrid laminates improved the buckling and failure load about 9% and 17% respectively compared to the conventional QL layup. But if we look the force and the displacement curve on the right-hand side, we can still see the gradient are different between the simulation and the experimental data. The reason for that could be there are maybe three different reasons to explain that. The first one is material properties, because in the simulation we use the material properties of the unidirectional fiber, whereas when we manufacture the laminates, we use the woven fabric, and also the imperfections in the manufacturing and testing process will cause this difference because maybe the surface of molded specimen is not completely flat, and the different in tightness of the bolts around the frame and the clamps may create some distortion to the specimen. And also the voids in the specimen can also reduce the failure strength. Then the next step, which is ongoing now, so we at Bristol to use their CTS machine to reproduce our steered pattern we found in our project and to manufacture the composite, and we will do the comparison test in the near future. So now we know the steered fabric can offer the better buckling resistance property on the flat panel compared to the conventional QL laminates. And we also found the numerical and the experimental results have the good agreement. So the next step is we want to explore the application of the steered fiber laminates on some typical structural components through the numerical simulation. But the first step, we need to make sure our mapping of the fiber orientation and the thickness of the fabric is correct on the numerical model. So to test that, we give a mapping trial. So we want to map the steered pattern correctly on the web section of the I-beam on the box beam, and also map the 2D steered pattern correctly on the cylinder. So here's the result. We can see the fiber orientation of the steered pattern we generated is correctly mapped on the finite element model in Abacus. So, but now the Lee and Paul, the two new research assistants, are still doing the investigation about the optimization of the mechanical properties on the air beam, sandwich structure, and cylinder. Okay, that's all. So in conclusions, in this project, we proposed a new fabric steering technology by aiming to reduce the cost and improve production rates of the current AFP method. And we developed a new design tool, which is called SteerFab, and it has been used to demonstrate the numerical design and analysis of the SteerFab laminates panel and provide manufacturing guidance for this technology. And this technology also offers a move towards the high volume production because it has a capability to simultaneously manipulate the multi-layers of the fabrics and it's shown to be repeatable and controllable by using a multi-point manipulation method. The production rates can be further improved by using a bespoke fabric, which is developed in the University of Manchester. And according to the both numerical and experimental investigation, we found a hybrid laminate of the better buckling resistance to compare the QI laminate. And in the future, we need to further explore the application of the steered-fibre laminates on some typical structure components. Okay, that's all. Thank you. So if you have any questions.
Hi, thank you, Zhaofei. Right.